Okay, let's get started then. So, hi everyone, welcome back to our Attack Detection Fundamentals series. We're going again for 2021. We've got a ton of content for you today. So I'm going to go through just a brief overview of the workshop structure, I guess, for this year, some of the changes that we've made, and then we can get started on the main event. Just a quick note to say that there's a Q&A in the Teams chat, so feel free to ask questions. We'll endeavour to answer them as we go along, and if there are any left over, then we'll try and round them up at the end as well. So let's get started then. So I'm thrilled to say that I'm joined again with Riccardo. So Riccardo and myself will be taking you through the session today. Riccardo and I are both security consultants at F-Secure Consulting. Riccardo leads the Active Directory security service, and I lead the attack detection and all things purple teaming services for us as well. So in terms of the goals of the series, I think you're probably or hopefully familiar with these. So fundamentally, we're trying to improve everyone's understanding of attacker techniques, how we can detect them, how we can prevent them, and hopefully provide some level of kind of fundamental understanding, a little bit of a peek under the hood when it comes to how enterprise products work, and certainly the ones that you're using day to day, so you can get a better understanding of what they do and don't do for you. In terms of how we're going to do it, the format of the series, so a simple kind of premise, I guess, is we're going to analyze a set of known TTPs. We're going to emulate them in a controlled lab environment with some video demos. And then we're going to observe the traces that they might leave, the opportunities as defenders that those traces might provide for us in a detective perspective. So just as before, we're trying to keep things as simple as possible when it comes to the lab setup. So for most of these labs, we're using one or maybe two virtual machines. Intentionally, all of the tooling that we'll use, both offensive and defensive, is going to be open source. And with that, there's some shout outs to just some of the shout outs, in fact, to guys like NCC, SpectreOps, MDSec, Palantir, and FireEye for the both offensive and defensive research and the tools that they've put out that you'll see on display today. And then also to kind of help you I guess, digest this content, we've got in this case 4 lab scripts that are provided and they're live now, so you can go and have a look at those in your own time and work through those labs. Feel free to ask any questions either directly on Twitter or on the YouTube videos themselves. But the idea is that all of this content will be available for you to digest in your own time, so feel free to watch the recording. We'll make the slides available as well, and you can go through that as you need to. We just based on the amount of content we've got here, we might run over ever so slightly today. I know we've got 1 hour, but if we do, then again, all of this content will be available after, and you can go through if you do miss the end. So the structure then, slight change from the 2020 series. So rather than go through a kill chain as we did last time, focusing specifically on Windows endpoint, we're going to do things slightly differently and cover a few different technologies, so broaden our scope a little bit. So Riccardo and I are obviously here today for our session on Windows, and then we are joined next week for a macOS detection course with Callum and with Luke. And then the week after, I'm back again with Nick Jones to go through some AWS flavor detection. And then finally, on the 28th, we round out the series with Masande, who'll be going through some Azure-based detection. So workshop 1, then Windows. So the obvious question is, did we do this last time? We've gone through the kill chain. What's going on? Well, my hope is that this workshop is going to both build on the things that we did previously. So as I said, the last 4 from 2020, which are still available for you to watch if you choose to. We went through the kill chain and covered a fair bit of the concepts behind our detections, as well as the TTPs that you could look to detect. This time, we're going to deep dive into some of the areas that were maybe touched on less, so in defense evasion and credential access, and hopefully provide a bit more of a deep dive into some of the background of EDR, kind of endpoint detection and response. So being endpoint focused, the obvious telemetry sources we're going to be drawing upon are endpoint logs. So there's some Windows event log and some honorable mention of Sysmon. And there's also a deep dive into EDR, and then again, some mentions of AMSI and the like. So a few things there. In In terms of this workshop, the structure, we've got kind of 4 key areas, I guess. The first is EDR and its limitations. So we're going to go through kind of what an EDR consists of, what the actual technical components are, and by virtue of that, what its limitations might be, some of the ways that attackers are kind of pushing back on that. And by that, we're going to look at the common evasion techniques that they might be using there. And then we're going to look at a bit more, I guess, post-exploitation. So we're going to be looking at some userland hooking, both offensive and defensive. And we're going to be looking at some cookie theft and session hijacking. To do that, just as before, we've got our 3 labs. The first lab is going to cover the construction of an initial access and session prepping payload. That's quite an in-depth lab, so we've actually split that up in the lab guides into 2 separate entries. And then following that, there is an offensive API hooking demo using MD6 RDP Thief. And then lastly, we have our 3rd lab, which is going to cover cookie theft and session hijacking, like I said, and that's going to use Rich Warren's CHLONIUM project. So with that, I'm going to pass over to Riccardo, and he's going to take us through EDRs and their limitations.
Yeah, so first of all, hi everyone. So we figured that before starting to dig deep into the latest and greatest bypasses, it might be worth just discussing what an EDR is and all the components, really, because all the products might be different, but to a really high level, they're all composed by the same pieces. So this is a really high level definition, and I appreciate that. But EDR, or endpoint detection and response, they're usually software that are meant to be executed on the endpoint, are meant to detect and to prevent, respond to threats. Of course, as I said, the complexity and efficacy varies a lot from product to product. However, at a really, really high level, they're all composed by 1 or more kernel drivers, set of dynamic link libraries, and a Windows services, 1 or more Windows services, actually. So let's start analyzing the kernel driver. So usually it's the core of the actual detection engine, but most importantly, they use to register what is called a kernel callback. So they're just notification for specific events that might occur. For example, process creation. It's an interesting one, and also they can register 1 or more mini filter. So they're just other drivers that are meant to intercept requests. So, for example, the file system mini filter. It's something that EDR and in general AV defensive product use to, for example, protect their installation components like the eVirus CXC and DLLs. They're kind of protected. So if malware or an attacker is trying to delete them, usually mini filter kicks in and prevents that from happening. So the other component that we described is the Windows service. So Windows services, they can be used for communicating with the actual kernel driver. So Windows services, of course, they're USERLAND component, so they can interact with the kernel land by the kernel driver that we talked about before. But also, they're quite interesting because they can be used to send back telemetry to the on-cloud or on-prem appliance. So all the telemetry and some alerting as well can be sent via these specific services. And the last component, and that's the one where we going to discuss a lot about, is the dynamic link libraries. So they're just DLLs that are going to be injected into USERLAND processes, and this is mainly done to achieve some sort of behavioral monitoring, and we will see exactly how that happens with code examples as well later on. So what it means, if we see this from an attacker perspective, when we want to get something running on an endpoint, an implant, for example, it can be either, I don't know, Cobalt Strike or Covenant, whatever. It means that we have to deal with every detection, every piece of the detection stack of the EDR. So if we want to be even more specific, that means that we need to bypass the static analysis. We need to bypass the emulation and sandboxing. So when you're dropping something like an exe on disk, some product, for example, Windows Defender, they will try to emulate that in a kind of a sandboxed environment to determine whether it's malicious or not. And even if execution is actually allowed, they will still apply some runtime monitoring and behavioral analysis using, for example, the dynamic link libraries injected into the processes and the API hooking that we'll analyze later. And of course, we need to egress from the network. So like when we deploy an implant in a system, we have to actually be able to communicate back to our command and control server. We'll not discuss the egress component because that involves other pieces like proxies and perimeter firewalls. And I said evading, but when I say evading, it doesn't mean that we're not going to generate any telemetry. That's pretty much impossible. It just means that all the actions that we want to perform are not going to generate alert and response as well.
Yeah, it's worth mentioning here as well, like we're just talking about that initial kind of code execution. And if we consider like the whole kill chain, when we talk about that kind of that defender's quandary of they have to succeed every time, an attacker only has to succeed once. This is that great kind of example, I guess, of where we're not even talking about how an attacker could go about escalating their privileges. We're not talking about how they could move laterally and kind of ultimately achieve some objectives. So there's plenty more to the puzzle, which we've kind of touched upon in previous workshops as well.
Yeah, exactly. Just the initial access bit. So let's start with the static analysis component. So for those who are part of a defensive team, they're pretty, they know these tools because they're quite popular. So for example, if we want to get into the details, when you're dropping something on disk, that thing is going to have some specific indicators. That can be, for example, suspicious string or patterns, but other things like function import, function exports, and other things like that. From an attacker perspective, when someone is trying to develop a payload that is meant to bypass static analysis, they will need to take care that the thing that will drop on disk, if they will drop on disk something, they will pass all the basic checks of the static analysis. So for example, they can use tools such as Yara or Kappa to do some basic triage of their payload, just to see if there is no obvious thing that might get their payload flag and deleted from disk before actually executing it. So in the specific example, we're using Yara, and we're using the FireEye's Red Team tool countermeasure repository, and we're scanning Cobalt Strike beacon shellcode. And as you can see, we have a hit, but that's of course expected, because that's what the rule was meant to be. But this is just for saying that, so for example, if you embed the Cobalt Strike shellcode or another shellcode for what it matters into a, like we will see later, shellcode injection program, and you embed the shellcode in, let's say, clear text, so without any encryption or things like that, that's something that will be captured by EDRs or even basic AV, like even Defender can pick up the Cobalt Strike shellcode being embedded in clear text. So that's something that should be taken into consideration. Another quite interesting tool is FireEye's Kappa. So it's just a tool that tries using some sort of static pattern matching to identify what are the capabilities of the sample that you're trying to analyze. So in this case, I wrote a DLL that was doing process injection in kind of a more stealthy way. So you can see that Kappa was able to identify that it was loading things from the resources using Win32 APIs, because the shellcode was stored in the resources section, and also the creation of a process in a suspended state. I mean, Kappa has a lot of false positive if the sample that you're analyzing and you don't know if that's malicious or not. But if you know that's already malicious, then you can use this indicator to either, from an attacker perspective, improve your payload, or from a, defender perspective to better understand what it does in a quite a simple and easy way. So another interesting thing that we already mentioned is the function import. So when you're writing something, a program for Windows that's using a function that's exported by a DLL, you can basically do that in two ways. So using static linking or dynamic linking. the most basic form is the static linking. So if you just import libraries and you reference and you just write the function name, for example, message box, that's probably using static linking. So when you're using static linking, what you're going to do is actually populate the import address table, and that's something that's going to be reflected in the P file, the exe or DLL that you're going to write on disk. And that can be suspicious if you're using, kind of dodgy APIs. So for example, here in the screenshot, you can see that the sample was clearly doing process injection, because you can see functions such as QUse or APC, write process memory, virtual allocx, create process, and things like that. So quite suspicious. And if you drop something like that on disk, it will raise some flags, certainly for Defender at least. So what could we do to, I would say, improve that? Is that using, thank you, is to use dynamic linking. So we can use something like get module handle and get proc address to retrieve at runtime the function pointer of the function that we want to use, or we can even use the process environment block parsing to avoid even using those two APIs. So there are better ways of doing that. So if we go on, we will see another interesting thing. So, and it's function exports. So when you're writing something like a DLL, you might export some functions. So one quite interesting example is when you're writing reflective DLL. So reflective DLL, for those not familiar, are DLL that are meant to be executed from memory and not dropped on disk. An interesting fact is that they have to export a specific function called reflective loader that will take care of the self-bootstrapping in memory. So that's why they can be executed in memory rather than dropped on disk. Now, if you use the default reflective loader code, the exported function will be named reflective loader, quite surprisingly. So that's something that can be used as an indicator. And an interesting thing is that, for example, COBOL strike, when you're using a post-exploitation module, so for example, either Mimikatz, keylogger, or screenshot, or things like that, what you will do is effectively injecting reflective DLL into new process or into existing processes. But the reflective DLL that you will inject uses the reflective loader function without modifying the name of the exported function. So it's can be easy to identify those type of things. Even with a basic Yara rule, it's pretty simple. So another, I would say, more advanced way of doing that is to use the shellcode reflective DLL injection project from Silent Break Security. So what it allows you to do is basically, instead of exporting a function like the reflective loader, it just appends the reflective loader stub in front of the DLL code. So you don't have to export anything specific, and you can use literally any DLL that you want. Of course, the bytes that are associated, you can see on the screenshot, associated with the self-bootstrapping code, they are signatures for those specific byte, but it's less trivial than having the reflective loader exported like that. Nice. So go on, Alfie.
Yeah, so I guess up until this point, we've kind of seen like what an EDR consists of, and we've mentioned a few things when it comes to how it does its business, how it generates its telemetry. We talked about the DLLs and how they could perform some API hacking, etc. So just going to spend a bit of time now, I guess, just looking at some of the evasion techniques that are commonly employed to try and bypass kind of next-gen AV, EDR products as a general kind of concept, I guess. And the three that we're going to spend some time on are process injection, anti-sandboxing, and a kind of combination of process ancestry and mitigation policies as well. So just to get started then with the high-level concept of process injection, I think there's probably the two most obvious forms of this are local process injection and remote process injection. As the names might suggest, local process injection is where you're taking your shell code or your position independent code, and injecting that into yourself as a running process. So a good example we've got here is with a VBA macro. So if you were to take an embedded shellcode within a VBA macro, when you launch that, and it's obviously written accordingly, it will allocate, write, and launch that shellcode all within the Microsoft Word, as an example, process. There's a few kind of good things about that. There's no spawning of new processes. There's no kind of reaching out to existing processes and obtaining a handle and injecting into other kind of remote processes. So in that sense, I guess, arguably, it's more OPSEC safe from an offensive standpoint. But what it does mean is that if you're kind of reaching out to a C2 server, for example, that it will be that compromised process, that kind of WinWord exe process that's making those calls, which in itself could be something of interest. We certainly looked at that in one of the labs last year when it came to an XL, a sharpshooter payload doing the same thing. And then there's the remote process aspect of this as well. So in some cases, you actually have to move to a remote process to do some of the post-exploitation you might want to do. As we'll see when it comes to compromising an RDP session, to do that, we need to migrate or at least inject some shellcode into the RDP or MSTSC process to do it. When it comes to our options as an attacker, as an offensive operator, most C2 frameworks worth their salt provide us with shellcode that we can inject, and that is a good level of operational flexibility. We've already mentioned this idea of packing them into a macro, but just as easily we could put them into any format that we choose to. So some examples here. So firstly, a local shellcode injection. There was a blog post out by NCC's Rift team, I think in January, where they looked at some of the macros from the Lazarus group. And there was some, I guess, you would say, innovative uses of callback functions that allowed them to execute their shellcode in a rather, again, arguably novel way. So there's an example on the right-hand side and a link to several other callback functions that could be abused in this way. And then the remote process injection front, we heard about this idea of dynamic linking and how rather than having your static imports there, you could get them dynamically. And what we're seeing here on the right-hand side is a good example of that. So this is a port of the Wover and FuzzySex deinvoke library, so tiny sharpsploit as it's been coined. And you can see there, if you just go through, you can see the names of some APIs that we actually saw in the imports table previously. So we can see the create process, we can see write process memory, we can see the queue user APC at the bottom there. And what we can do with the tool that's mentioned here, so gadget to JScript, is to take our .NET code that's essentially going to inject our shellcode, and we can wrap that. In this case, we're going to be outputting in the example code there to a HDA file, so something that we could potentially deliver to an endpoint, to a user that they could launch, and then from there we could obtain a foothold. So just a couple of examples of the local and the remote opportunities that this could provide us. From a defensive standpoint, then, what can we do when it comes to EDR and with AV? Well, there are a few things. So the first is one that we've already mentioned, this idea of those security product DLLs providing us with USERLAND API hooks. So if we start making calls to, as an example, to write process memory, there's a reasonable feasibility that there is some API hooking. Obviously, again, as Riccardo said, depending on the vendor and the application, the kind of implementation. So that could be something that when we try to write process memory, we try to obtain a handle, we try to launch a new thread, that those function hooks will intervene and say, okay, can we identify the kind of whether there's some malicious intent here, and can we act accordingly to actively prevent this from happening, or just to alert upon it potentially. There is a concept of kernel land hooking, but that was kind of nipped in the bud a bit by Microsoft with PatchGuard or kernel patch protection, or KPP. Other opportunities, USERLAND ETW. This is something that we touched on a few times in the previous workshops when it came to .NET, when it came to LDAP queries as well, and we'll see some more of that in just a moment. Riccardo also mentioned the idea of kernel callbacks as well. So regardless of the, as we'll see, some of the defense evasion we can do to bypass our USERLAND hooks, if there are kernel callbacks in place, they could still provide our endpoint products with visibility of those things taking place. And we saw an example there of a new process being created and triggering the kernel callback, regardless of what kind of USERLAND defense evasion we might employ. And then the last one that's quite interesting is kernel land ETW. So we've mentioned userland ETW, and as you'll see in the lab guides, there's some mention of trying to bypass that telemetry source and try and prevent it from producing logs that could catch us as an attacker. Kernel land ETW provides us with, as the name suggests, those ETW events directly from kernel land. And one in particular that's quite interesting is Microsoft's, I guess, reasonably recently introduced threat intelligence feed. So if you tap into this feed, you can see an example here. So on the left-hand side, Riccardo has been so kind as to screenshot one of my tweets here. But effectively, one way of bypassing userland hooks is to use direct syscalls. And if you've been following kind of offensive security Twitter for the last 6 months or so, if it's not API hooking that we're talking about, or API unhooking, I should say, it's direct syscalls. So in this example, we've got a remote process injection using the NT map view of section and the NTQ APC threads, and we're using direct syscalls to directly interface with the kernel. The idea being that if there are any high level or even low level API hooks in place, we can bypass them completely. And what we're seeing on the right hand side is a couple of screenshots here of the output from the threat intelligence ETW feed, which is providing us with pretty obvious evidence that one process has mapped a view in another, and then subsequently we can see the call to queue user APC as well. So some pretty high value ETW events that we could be consuming as an EDR there. Anti-sandboxing. So again, as Riccardo mentioned, if either you're dropping your malicious file onto disk, or it's being scrutinized by an analyst, whatever, sandboxing gives a quite quick way of evaluating whether or not the intention of that executable is malicious. And there's an example, as you can see here, using FireEye Speakeasy to emulate the API calls as a Cobalt Strike beacon is being launched. And you can see that it's spawning a pipe there. And if you followed like some of the identifiers of Cobalt Strike, you can see that MSSE name in the pipe is something that is indicative of Cobalt Strike, and is something that's configured within the artifact kit of that framework. So what we can do as an attacker or as an offensive operator is provide some anti-sandboxing capabilities within the payload that we produce. So as a very, very simple example, that could be ensuring that our endpoint that we're targeting, that we're being launched on, is domain joined. That could even go so far as to say it's the specific domain that we're targeting, for example, and that kind of thing can just add another hurdle when it comes to trying to emulate that in an easy way. The whole concept of sandbox evasion and defense evasion like that is a field into itself, and there's lots of resources on that I'd recommend that you go away and look at, because there are endless opportunities to implement sandbox evasion techniques there. Something else as well, so a bit of research from XPN, Adam Chester. So the idea of applying a mitigation policy to a newly spawned process. So we touched upon this idea of remote process injection, and we also saw the tiny sharpsploit kind of sample there, where it was spawning a new process, and then we were going to inject our shellcode into that process to obtain probably a foothold of some kind. A couple of mitigation policies you can apply to a newly spawned process. So the first one will only allow DLL signed by Microsoft to be loaded into our new process. And the second one will prevent the allocation of read, write, and execute pages. So the first one's probably quite an interesting talking point. So the idea here is that if you take any EDR provider that's using a loaded DLL to provide some level of their security functionality, be that API hooks or otherwise, if that DLL isn't signed by Microsoft, then there's the potential here for your mitigation policy to prevent that DLL from being loaded, and by virtue of doing that, prevent any kind of telemetry or hooking from having an effect. To be honest, I think as we kind of progress from here, you'll see that most security products, or kind of certainly a lot of them, are cross-signed by Microsoft. So the likes of CrowdStrike and Symantec, to name a few, are cross-signed by Microsoft, meaning that if you apply this, as it's commonly called, block DLL's process mitigation policy, it will have no meaningful effect to that DLL being loaded. But what it could do is work kind of against you to say, as an example, if you're an Internet Explorer process and you're the only Internet Explorer process in the entire target organization that has this block DLL's mitigation policy applied to you, that could obviously make you stand out and actually provide more scrutiny than you otherwise were hoping for by doing that. So quite an interesting thing that could be employed here. Parent PID spoofing. So if you look at, I guess, a lot of detection kind of fundamentals, really, we look at the idea of parent-child relationships or process ancestry. The idea here being that if you end up with kind of anomalous parent-child relationships or things that you know are, I guess, known bad, that can serve to be a detection in itself, regardless of any kind of subsequent activity that might be taking place. A good example, again, depending on your environment, could be something like this. So we've got a Microsoft Word or the WinWord.exe process that spawns PowerShell. This is something that, again, we did in the first workshop of 2020, where we had a macro in Word that was spawning PowerShell. Now, if that happens, again, depending on your organization's use of macros, it might be that is straight off the bat, you know that's going to be a problem and you're going to act accordingly. Well, the concept of parent PID spoofing is to modify that process when it launches, such that parent-child relationship is kind of obfuscated to some degree, and it looks as though another process that maybe is more expected as the parent, it takes its place. So you can see here, as an example, Explorer is reported to spawn PowerShell rather than the Microsoft Word process. And there's a mention here as well for Will Burgess. So there's a Wild West Hacking Fest talk there, Red Teaming in the EDR Age, that covers this concept, and several others as well that's worth a watch. And there's also some associated research as well that we put out on detecting this. So you can see here, using the Microsoft Windows kernel process, the ETW feed that is, you can clearly see the mismatch between the process IDs that are reported there as to what the parent is. So if you have the feed available to you, and as an EDR provider, there's a high chance that you do. This is a way that you could trivially spot that taking place. But if we just look at it from a kind of process creation perspective, it might be that we can evade some of the rules that are in place there. And then I guess just to mention at the end of all of this as well is, obviously we've talked about some kind of defense evasion techniques, but even when we've got a successful launch of our shell code, it's running in memory, we've got a C2 potentially, there are memory scanners that can detect the profile of our payload in memory as well. So there's some good mentions here of some open source tools that allow us to kind of spot some anomalies, not only in our maybe, I guess, indicators that we've performed some injection, but also, as we'll see, certainly in the labs of this workshop, cases where we might have tampered with the functions in other DLLs as well. And there's a series of references at the bottom there. And just to remind you that we'll have these slides available as a PDF on the event website as well, so you can download these and click through those links at your leisure as well. So, Riccardo, USERLAND hooking.
Yeah. So we mentioned how EDRs can install USERLAND hooks to perform, process monitoring. So what it actually means is that EDRs and in general security products are interested in identifying where software use some specific endangers APIs that are commonly abused. An example, probably the most common example, could be like the create remote thread, or QUser APC functions that are commonly used by malware. So what EDRs will do is hook those functions and try to determine, using their engine, whether the invocation of that API is malicious or not. So now we don't have a commercial EDR to show you here, so we're going to use an open source product called Frida to actually perform API hooking and show you how this looks like in memory. So syntax of Frida trace is pretty simple. We specify the process ID that we want to inspect and the function that we're interested in seeing when it's called and what the arguments are. So in this example here, we're invoking we're hooking the create remote thread API. But if we, for example, take the VBA code that Alfie showed before for doing process injection using callbacks, for example, we could do the same with Frida. So if you see the -e parameter now specifies the function that we're interested in hooking, and as you can see from the Frida output, we can actually see the API being called. I mean, it's not extremely exciting now because, of course, Frida doesn't have any decisional engine inside that can decide whether the invocation is malicious or not. Of course, an EDR might do something more about that. So we mentioned API hooks, but how this looks like in memory and how this is achieved. So it's the technique that is usually used. It's called trampoline, and basically consists in rewriting the first bytes of the functions that you want to intercept with a unconditional jump to a separate module. Usually the module where the function is going to jump to is the one that belongs to the EDR. In this case, it's the module that belongs to Frida. So the Frida module will receive the API call, and it will be able to inspect all the parameters and take some decisions based on that. And after the decision is taken, they can just restore the execution flow, and the execution, if it's not malicious, can continue. And you can see in the slide, it's pretty simple. However, we should say that despite it's the most common technique used by EDRs to inspect APIs and in general detect process injections and things like that, it's probably the worst. At least in general the model, the detection model used by USERLAND hooks, it's kind of broken, because the thing is that, as we already mentioned, USERLAND hooks are implemented in DLL. They're loaded into the target process memory, right? However, within Windows, every process has full control over its memory space. That includes the EDR DLL. So what it means is that the target process, if it's infected and malicious with, I don't know, whatever, Cobalt Strike, they can just remove the hooks. And if the EDR only telemetry for detecting process injection is based on USERLAND hooks, they're going to have a bad time, I guess. Of course, it's not the only way, but it's probably the most popular and cheap way as well to do that. So how do we go about removing these hooks? So Alfie already mentioned one way of doing that, and that's using direct SYSCALL. So it's just avoiding the hooks and talking directly to the kernel. However, we can remove the hooks using various techniques. So as an example, we can just overwrite the bytes. So as we've seen before, the bytes were overwritten by the EDR using a jump. We can do the same and just restore to what it used to be, since we control that memory space, since we're hooking our process we control. Another way, which is a bit more generic, and honestly, I just prefer that, is refreshing the hooked DLL. And that's a research that has been published by SYSCALLS. Basically, what it means is that you're going to take the in-memory DLL and just replace it with the on-disk version. And the thing is that the on-disk version, it's not going to have the hooks because the EDR don't modify the on-disk NTDLL, for example, or kernel 32, because otherwise it's going to just break the whole system. Another interesting way of doing that is manual mapping the DLL. So instead of loading the DLL in the classic way, they just kind of rewriting the P loading process and you just invoke the function from the mapped DLL. And that's something implemented in the deinvoke framework published by Fuzzy Security and Hoover. A good reference for these techniques can be found on the Cobalt Strike blog, Push It Back on USERLAND hooks. And that's quite interesting, quite an interesting read. So we mentioned the DLL refreshing, and just to tell you, we're going to analyze that specific technique. So just to reiterate, what are the advantages? So we mentioned that the technique consists of just swapping out the DLL that we have in memory with the one that's on disk. The advantage is that we're going to remove all the hooks from the DLL that we're going to do, let's say, refresh. Okay, so we don't need to know the bytes that we want to replace, because of course, when we have a jump that we want to override, so a hook that was in place, we had just put random bytes, because otherwise it's going to crash the function. And you don't even want to take the chances of using what's on your system, because that might change from system to other system, so it could be kind of dangerous to do. So this is quite easy. I mean, the code itself looks a bit complex, and this is taken from the iRev team website, but in 20-ish lines of code, you can effectively remove all the hooks from, in this case, it was NTDLL. So, and it's quite flexible, so you can implement it in different languages, and at the end of the day, code is there, so pretty simple to use. So let's start with the first lab.
40 minutes in, I'm going to do a lab.
Oh, yeah. So let's start with Covenant. Okay, so quite popular command and control framework. We have our listener running, and we start by generating a launcher. We chose to generate an exe launcher, and we configure the .NET target that we want to use, and download the exe on disk. We're not going to use the exe directly, of course, because it's not that basic, this workshop, right? But we're gonna use Donut, which will allow us to convert the Covenant exe in a shellcode, and this will include the AMSI bypass, since the machine that I'm using also has .NET Framework 4.8, which has AMSI introspection as well. So quite simply, we can just generate the payload. Yeah, I think the video is just it's just doing whatever it wants, right? Okay, so we have the shellcode here. We just use a small utility for doing process injection. That's, of course, all the references are in there. But now that was just to test our, if the shellcode was working. This is the actual process injection we're going to use. It's quite basic, so it's still using the create remote thread. So what it does is just create a suspender process, allocate some memory within it, write the shellcode, and you can see on the bytes that I'm highlighting with the mouse here. And then we create a remote thread that will point to our shellcode in the target process memory. To generate the shellcode in the bytes format that we've seen in the source code. And by the way, it's just a DLL code, and we're going to publish everything later. It's nothing too advanced, honestly, but it does its job. I wouldn't use that on an operation, but using the xdump command, it's just so easy to take the bytes and just include that in the source code. Now I will just test if everything is working. I'm not compiling it here, but feel free to do that on your own. I will use process hacker to inject the DLL into a running notepad process, and I left a message box there for other debugging processes. And you can see that a new notepad process is spawned, and the shellcode is injected, and we can actually see the ground. Now, what I will do is use an HTA to trigger the DLL load process, and this is just to show you here just a different way of loading that DLL, and that's how we're going to do in the lab. So what I'm doing here is just take the process ID of the MSHTA process, that's the one responsible for managing the HTA, and using free.race, I hook the nt-threadx function, which is the underlying function used by create remote thread. So you can see that the function was actually used. I mean, an EDR would probably have done a much better job in, probably stop the process. But now you'd see that I will go back to Visual Studio, and as we've seen in the slides, we can use the unhooking code and target the in this case was the 32-bit version of NTDLL. And we will just compile the DLL again, and basically we will just repeat the whole process injection thing, but still using free.race and in this case, we shouldn't be able to see anything suspicious happening. So DLL is compiled. We just spawned the same MSHTA and inject using Frida again. So I was using an alert function just to allow me to hook the HTA before exiting. So process injection happened, nothing on Frida, so meaning that we bypassed the hooking, and we also obtained an implant on the system. Quite simple.
If I can get the video to play properly.
maybe, you know. So what it means, does it mean that it's like basically game over for EDRs? So not really, or at least not for the good ones. So as I said before, if an EDR only way of monitoring processes is by using USERLAND hooks, and some of the cheapest product probably will still do that. But otherwise, these type of products, they have multiple ways of detecting this type of things. So just few examples, and there are many more. So Alfie already mentioned the kernel threat intelligence CTW, so that's quite powerful, I would say. But also there are other kernel callbacks that you can register, for example, for the create remote thread activity. And for example, the sysmon event ID 8 is just about the create remote thread. So that's just, you know, another way of detecting that specific type of malicious behavior that some of these products may employ.
Nice, cool. Okay, so at this point, I guess in a hypothetical, you know, a kill chain, we've made a payload that can bypass a series of the security controls that might be in place from an EDR or an AV. And now we're going to look at a couple of post-exploitation techniques that we can use. So the first thing we're going to look at is again this concept of API hooking, but looking at it in quite an interesting offensive application. As I said, that will be using MDSec's RDP for that. And then we're going to look at the cookie theft using Rich Warren's CHLONIUM project. So offensive API hooking. So we already understand this concept from, as Riccardo said, when it comes to loading a DLL, and that DLL is going to add a trampoline or a jump function into the API functions of interest, and then perform, you know, some logic following that. In the EDR's case, that could be a go, no go on whether or not we allow that function to be called kind of unimpeded. But in offensive cases, we've seen this used in kind of info stealer, kind of banking Trojan type stuff to compromise sensitive information. And that's exactly what we're going to do in our demo. So if you take a look at the MDSec research on this, you'll see that when, as an end user, we interact with the remote desktop application, the MSTSC binary, when you authenticate to a remote host, there are three pieces of information that you typically will pass on. The first is kind of where you want to go, so the IP address or the host name, and then subsequently the username and the password. Obviously that username could be a standalone username, that username could be a domain joined account as well, but regardless, that information will pass through MSTSC to achieve that connection. And in that research, we can see three APIs that are of interest, each one handling a different kind of component that we are looking for as an attacker. You can use, as an example of a tool you can use here, you can use API Monitor to achieve this. In the blog, the kind of lab guide that covers this, we'll do it both with API Monitor, and there's also, again, a script from Fuzzy Security that uses Frida to achieve the same thing. So you can see here, this crypts protect memory, and in the right-hand side there in the red square, you can see Riccardo's terrible password that he's using to authenticate with a remote host. And there are a couple of examples of this. So I guess one of the very simple ways of performing API hooking in this way is using Microsoft's DTORs library. So RDP Thief uses that, and similarly, Fuzzy Security has another implementation written in .NET called Remote Viewing, and again, there's a link there, and you can go and see that doing a very similar implementation. And obviously, goes without saying that I'd imagine that you could probably, you know, let your imagination go a bit and see where this could be applied. There's just a couple of references there to using it with targeting web browsers, and similarly targeting 2FA soft tokens as well. But again, use your imagination. There's many ways that this could be employed. So our second lab then, we're going to take a look at RDP Thief, see what it does when we inject it into our MSTSC process, and what it produces as an output. So I'll pass over.
Yeah, pretty short demo this time. So basically what we'll do is just take the RDP Thief from the MDSAC repository and clone it and compile it with Visual Studio. And in the blog post, it will be much more specific in what it does and how it's used. So we're going to use the shellcode reflective DLL injection against the compiled DLL that's going to give us the basically the shellcode that we want to inject into the RTP process. So we just spawned the MSTSC binary, take the process ID, and now we will use another shellcode injection utility called Urban Bishop from Fuzzy Security that just allows us to inject the shellcode into a running process into using some kind of interesting technique. So shellcode injection went fine, we hope. Now what we have to do is just try to connect to a remote server. I'm just using a random server here, really. Using password doesn't have to be correct because I'm not going to show you my password. But now what? 123 then. Yeah, it's just my Gmail password. So now what we're going to do is just so what actually RDP Thief did is create a file in the temp folder, in the users temp folder called data.bin. Which, if everything went fine, and since this is not a live demo, just a recorded video, it's gonna be fine. We're gonna retrieve the clear text credentials that we just entered. So pretty cool.
Nice. Cool. Okay. So slightly different kind of bit of post-exploitation now, looking at compromising browser sessions. So just a very high-level primer on this. The idea being that when we, as end users, kind of navigate around a website, cookies allow us to maintain some concept of state. So if you imagine kind of browsing like an e-commerce site as a good example, even before you've authenticated to that site, you can maintain a basket, you can add additional items into that basket and kind of get all the way to checkout before you actually have to provide a username and password for your account to kind of make that checkout. So this concept is obviously quite cool, and it's kind of how the internet works. But it gets more interesting when we consider how this works with authenticated sessions. So you can see here just an example. So I've captured a web request to an authenticated session to GitHub, and this is just using Burp Suite. So you can see at the bottom there, having authenticated, I'm providing this cookie information to GitHub so that it knows kind of who I am, that I've authenticated, and I have an active session, and I'm able to access the information that it is that I'm obviously requesting. So effectively, whilst there are other things to note here when it comes to kind of obviously the source IP that I'm using to access a web service, as well as things like the user agent, this cookie provides a huge amount of information, or has a huge function within this web request when I make it, to make sure that GitHub provides me with the authenticated resources I'm after. So we can attack this as an offensive operator. So the way we do that is to access the cookies on an endpoint. So again, assuming that we have a compromised endpoint, we've gone through all of the advice that Riccardo's given us up until this point to obtain that foothold, we can try and target these. And the way we do that is to retrieve the cookies from their database, and these are encrypted by the browser. So in this case, we're going to be targeting Chrome, and again, as I said, using Rich Warren's CHLONIUM project. So the idea here is that the cookies will sit in a database on disk, and they're going to be encrypted, so they're not just kind of obviously plain text and there for the taking. And the way in which they're encrypted is using DPAPI, or the Data Protection Application Programming Interface. And we won't go into the depths of that. There's a great blog kind of reference from Harmjoy there as to the offensive applications or kind of the guidance, I guess, when it comes to DPAPI and how to use it on an engagement. But what it's doing effectively is providing like a transparent way or an easy way for Chrome to protect this information without handling some kind of key management or whatever. So on the endpoint, running in the context of our target user on that endpoint, we can use the CHLONIUM project, here we go, to extract the key that lies within the local state file. Again, we'll see all this in a moment. And from there, we can extract the key, we can take the cookie database, and with those two components, we can move over to our attacking host and perform that session hijack, effectively impersonating our user. So just as Rich says there, from Chromium 80 upwards, these cookies are encrypted, AES-256 GTM, and that's stored with a master key in local state. So what we're going to do, just to recap, is from our compromised machine on the left, we're going to grab the cookies database. As I say, this is a simple file on disk, and move that over to our attacking host. In our simple demo, we're just going to use a shared folder between our two virtual machines. Obviously, in a legitimate kind of operating scenario, you would probably be using a pre-established C2. And as well as that, we're going to use the local state file, again on disk, and within that is our encrypted key protected with DPAPI. We're going to decrypt that and take that material, that key material, and move that over to our attacking host. And then from there, we're going to use the other component of CHLONIUM, which is the UI component, to take both of those and import them into our own attacker instance of Chrome and access, in our case, our compromised user's GitHub account. So let's get started on this one. So you can see here, I'm on the target host. And I've authenticated, so my purple party user here has one repository, and he's already gone through the login procedure there. And again, just to reiterate, this has been done in a super simple way. So we've literally got CHLONIUM and Mimikatz of all things on our desktop. So maybe not quite representative, but the important part is there. So we can see running CHLONIUM, by default, it's going to use our Chrome install, so it can target other Chromium-based browsers. So the new version of Edge is a good example of another one we could target here. So there we can see our master key, which we can note down for later. And then I'm just going to quite simply use the copy command to take the cookies database and put it into my shared folder. So that's taken place now. So I've got both things, master key and my incredible movie maker skills there. We move back to our attacker host. My cookies database and a master key in hand. We launch the Chromium UI. Obviously, you can see on the right-hand side that I haven't authenticated to GitHub. I have no pre-established session there. And then I paste in the master key. I grab the cookies database from my shared folder. And then I'm going to close Chrome just so that I can import the cookies. So there I'm just going to specify import these into my version of Chrome. Import, and hopefully we get a success window there. And then from here, all of these cookies have been decrypted with that master key and re-encrypted on my attacker instance. And then from there, when I browse to GitHub, if all's gone well, we should see, here we go. So I'm now authenticating as the purple party user, having not provided any clear text password or any username to achieve that. So I now have kind of unfettered access to the purple repo that was otherwise private. So quite cool. So what do we do about this then? Well, if I go back here, this is an answer. So firstly, worth mentioning, there is a great blog there from Dane Stuckey of Palantir on this concept. So what we can use is an SACL or a SYSCALL. An access control list contains ACEs or access control entries. And the idea behind these, there are two flavors, a discretionary ACL and a system ACL. And an ACE could describe what can or can't access a given securable object. So just jumping on a slide, the ACL specifies the control, or allows us to control the access to a securable object. And an SACL is going to be very useful for us because it allows us to audit the access to a securable object. And just some of the examples on what those securable objects are include files and folders. And so we're obviously going to be applying that to a couple of high value files for us, but could just as easily be applied to name pipes or registry keys or Active Directory objects. So for the purposes of our demo, we're going to implement an SACL on two files, the local state file, which we're going to need to access as an attacker to obtain the encrypted key material to decrypt our cookies database, and then the cookies database itself. In the lab guide, we go through an extra step here where the CHLONIUM project allows us to extract saved passwords as well. So when you save a password in a Chrome browser, that is saved within login data, and it's protected in just the same mechanism we saw here with the DPAPI and the master key. So we're going to apply it to those first two, and you can obviously do the third one in the lab as well. So we're back on our attacker box. This time we're armed with an adapted PowerShell script. Again, that's taken from Dane's blog. So the first thing we're going to do is enable the advanced auditing feature within Windows, so that we actually surface the 4663 event IDs for this SACL. So just going through, again, I'm just applying it with local group policy, but obviously if you're doing an enterprise, you might want to use something more scalable. So from here, we go to our object access subcategories there, and we can see the file system one there. So just going in here and looking at the explanation, we can immediately see this is what we're after. So it's going to use SACL. So we have to define the SACLs in addition to turning on this logging feature to actually provide the event IDs we're after. So for the purposes of this, I'm going to apply to success and failure, and we can move on from here. So with that done, we now need to apply the SACLs, and this is done from an administrative context. So here I'm just spawning a command prompt, and I'm going to launch it with an execution policy bypass, so we can run the script that we've got on the desktop there. So we launch that, and we can run our cookies SACL PowerShell. There we go. Okay, so we now have both pieces of the puzzle when it comes to our logging. We've enabled the file system logging, and we've enabled the two SACLs on our cookies database and on our local state file. So moving into our event viewer, just in the security, obviously this would most likely and should definitely be shipped off to your kind of log aggregator. But in this context, we could just look at it in the event viewer here. So we're going to run it just as before. So I'm going to open a PowerShell window and launch CHLONIUM to grab our master key. And in the background, as I run this, you can already see the number of events in that index have increased, so something's happened. And then just as before, we can copy our cookies database into the temp directory of our shared folder as well. So having done that, we obviously know where that leads on the attacking side. But if we just refresh this, we can see our object read events there. So there are several here. The first one is to our cookies database. And we'll go into this in just a moment, but you can see already some interesting information here. So we can see the target secureable object that we're trying to gain access to. And we can also see the process, obviously slightly incriminating in this context, that is being used to access those files as well. So you can see the user that's doing it, the process they're doing it from, and what they're trying to access. So just skipping on here, just as I said, you can see a ton of information here that can hopefully serve to build some meaningful detection. So obviously, if we're dealing with Chrome in this case, and the Chrome browser is making these object reads, we're going to get limited mileage when it comes to any detection there. But if we start looking at things like PowerShell or other compromised processes accessing these sensitive files, that could provide us an indication that some kind of cookie theft and ultimately some session hijacking is taking place. It's worth mentioning, we've talked about the idea of remote process injection. If we were to inject directly into Chrome and perform this malicious activity from there, then that detection kind of might degrade slightly. But as a general principle, it's a pretty powerful technique that we could use here from a defender standpoint. And just as it is stated by Dane in his blog here, there are tons of applications for SACLs. Some could be on kind of carefully planted files. So if we have some kind of honey tokens, in the previous series, we talked about kind of object access events, our 5140s, 5145s. A similar thing could be applied here. If we have on our file system some sensitive files in the C drive, for argument's sake, and we know that they don't have any legitimate business purpose, we could employ an SACL to detect the access to those. Similarly, we could use an SACL on a registry key. So if you're carrying out some kind of host-based recon, so in the Detection Challenging Paradigms podcast, just to go shout out there, there's a discussion made between Dane, Jared and Johnny when it comes to seatbelt, so the .NET assembly tool that can be used for recon there. So just as a well-crafted SASL on some of those registry keys that are known to be targeted by seatbelt. Just as an example in the reference there for finding out the versions of PowerShell that are installed, that can provide evidence of some malicious activity taking place quite early on in the kill chain. And lastly, some sensitive key material. So if we're talking like kind of cloud provider access keys, for example, if we see those being accessed by processes that are very anomalous, again, that might give us the opportunity to build some detections and hopefully detect some suspicious activity. But I guess with all kind of detection things here, your mileage may vary. So obviously try it out, kind of tune it to your environment and see what's viable. So conclusions then, that wraps up our content for this week at least. We've gone through, hopefully you'll agree, a ton of stuff here from an EDR and kind of what it consists of. We talked about the kernel drivers and the DLLs and Windows services. We looked at some evasion techniques, so our process injection, whether that's local or remote. We talked about some kind of sandbox evasion. We talked about some PID spoofing, that process ancestry and mitigation policies. And we also looked at some post exploitation, one with RDP thief, and two looking at some cookie theft using CHLONIUM. So, as I said, just to reiterate, the recording for this workshop will be available probably tomorrow, as will a PDF of the slides, so you can go through and look at that and look at the references in there as well. And similarly, all 4 of the lab guides are available on the labs website now as well, so you can go and look at those. And then that just leaves me to encourage you to join us next week when we have Callum and Luke joining us for a macOS flavor detection workshop. And you can sign up on the event website as well, that will be shared after this. But otherwise, that is it for us for today. Thank you for joining, and we're only 5 minutes over, I think, so we did a pretty good job. Riccardo, I don't know if you've had a quick look through the questions already.
Yeah, just finishing awesome to answer them.
Sweet. Cool. Okay. Maybe as we're 5 minutes over, shall we wrap up and then we can continue answering these questions in the background?
Yeah.
Cool. Okay. Well, thanks everyone. I hope you enjoyed it, and I hope you'll be joining us next week. Thank you.